All right, let's assume that you and your twin brother or sister are at NASA at the Kennedy Space Center. The piloting twin boards his rocket ship, and he has a wristwatch that he synchronizes to his brother, who's going to be in the control tower. Now, initially, both clocks are synchronized. The twin boards his rocket, fires up the engines, and shoots away at the speed of light, turns around, and then comes back to Earth. The question then is, what will the clocks read when both twins come back together? And what we're going to discover is that the lapse of time between the clock on board the rocket ship is going to be vastly different compared to the clock that was at mission control. So here is this little animation, and so we would like to know, there goes the rocket ship shooting by, and we can see that there's a difference in the lapse of time. So let's dig into this a little bit more. All right, an important thing to consider when we discuss relativistic time dilation and length contraction is our perception of time and length. If I have a clock with me, regardless of what speed I'm traveling at, whether it's below the speed of light or faster than the speed of light, the lapse of time will always look the same to me. And that's because I'm in what's called an inertial reference frame. In other words, each one of us has our own viewpoint of how we perceive the world. And that reference frame travels with us regardless of which speed we're traveling at. So it's our perceptions that determine the lapse of time. So for someone traveling near the speed of light, or even faster than the speed of light, the rate at which their clock passes will be different versus someone who is at rest. So in this animation here, on the left you see the time passage for a clock that is on a rocket ship that is traveling below the speed of light. And on the right we have an animation of a rocket ship that's traveling faster than the speed of light. Now, the important thing to note here is that the lapse of time as perceived by the pilots or the pilot astronauts is the same. They're not going to notice any significant change. Now let's switch to the reference frame at mission control, where let's say you're the pilot astronaut and your twin brother is at mission control. So your twin brother at mission control, it has a clock, and we can see that he has a certain lapse rate that the clock is moving at. Now his perception of what the clocks are on board the spacecraft is going to be different from his perception. So once again, we're going to use the animation on the left is a spacecraft traveling at less than the speed of light, but nearly the speed of light. And you can see that his clock is running a lot slower than the clock that was at mission control. Now, it's interesting that when a stationary observer at mission control observes a clock that is on board a spacecraft traveling faster than the speed of light, his perception of that clock is going to be reversed. It's going to appear as though the clock is running backwards. All right. So once again, remember, when you're a pilot astronaut looking at your clock on board your spacecraft, it's going to run normal. Someone who's at rest outside of your rest frame back at mission control is going to see your clock running backwards in time. And it's a matter of perception, or a matter of which reference frame that we are sitting in. So important thing that we want to be able to do mathematically is, how do we relate these different clocks together in order to share information with one another. I'm excited to announce the premiere of my new documentary film, Time is a Fluid That We Ride to the Stars. In it, I discuss how we will design and build a micro warp drive engine that will take humanity up to speeds faster than that of light. Be sure and hit that notification bell and subscribe button so you'll be alerted to when it's available. Until next time, see ya on my channel, HyperdriveX.